title. This is still a talk on cryptography, I promise. This is a talk about things that go wrong on managed runtimes with cryptography. It's really a plight to stop using C# and Java for crypto, but we'll get into why. So I know this is old, but it's still relevant to the conversation. This happened about a year ago-ish, close to a year ago, and the question came up at one point. Why don't we stop writing this stuff in C and use managed runtimes? Because given a managed runtime, Heartbleed would have never happened. Right? We wouldn't have had that problem. But this opens up a whole new world of problems when we go kind of really dive into it. Now, I want to set some expectations for this talk, because a lot of you start raising your hand and going, what about, and what about, and what about? Here's what we're going to talk about. This is what happens during runtime on JVM. CLR will kind of be applicable. We'll focus in on the JVM just because it's kind of hard to do both in the amount of time we have. But this is what we won't talk about. Everything else. So I'm not talking about people getting on your boxes. I'm not talking about stuff going over the wire. This is really a focused talk on just the internals of the runtime. We have lots more problems to solve than that. So yes, we have to solve those other problems too. But this is a deep dive into a narrow piece of this. So the other thing is intent. What are we trying to do with this? I mean, there's kind of the obvious thing. We want to keep sensitive data safe. That's the whole point of this. So if you don't want somebody to read it, what do? You know, we have a solution here. We encrypt this data. That's the easy story. But you know, let's say you hand this off to a developer, and the developer says, "Okay, I need you to go encrypt this." Right? Go. What happens? What do they do? What's the first thing they do? We go to Stack Overflow. How many of you know what Stack Overflow is? Okay, so for those of you who've never seen, it's a thing where you Google this thing, it's a programming thing I'm trying to solve, and up comes a bunch of answers that are all wrong. And then you copy and paste those answers, and then you have a thing that kind of works, but doesn't actually do the right thing. So we go to Stack Overflow, and we find this encryption code, and then we copy and we paste this. And I'll give you a second to look through it. So what I'm really looking for you is to count the number of things that are wrong with this code. There's some really obvious and some not so obvious. What's the huge problem here? The really, really big one. Bonus points to the rest. I heard it, I think. Right here? Des? That's a bad one, right? The biggest one is just using a really, really, really broken cipher core. But we've got some red herrings, right? We have an IV that's static. Doesn't matter, though, because we've used electronic codebook mode or ECB mode. That doesn't even use an IV. So that's a bad thing. So we have DES, we have using ECB mode. Our key generator is initialized with a static value. So our initialization for random numbers is 56, always 56. So we've kind of broken the whole world here. So yeah, this is really bad. Super unfair. I know. I get it. Yeah, this is not fair. But this is what we find when we go to Stack Overflow. I Googled, and I copied and pasted, and I cleaned it up for the slide, but that was it. That's what you find when you go to Stack Overflow. That's the advice that people, this is what people are doing. Now, we could pretend that we do all this right. We could write reasonable encryption. So I'll define reasonable for a second here, because there's a lot of people who have different opinions. Reasonable in Java is, it doesn't use string. Strings are immutable in Java. That you can't change them, you can't erase them, they lay on forever. You never want to use strings. We'll use a reasonable cipher core and block mode. So we'll go AES and we'll use something at a bare minimum CBC, cipher block chaining mode, right? Because it depends on your versions of runtimes and OpenSSLs and things and what they support. You know, GCM and that kind of things are nicer to have, but at least cipher block chaining mode. And at least a random initialization vector for each message. So we'll start with kind of the common default building blocks. And in Java world, we'll use the Java key store to manage our keys. So this is kind of industry standard default advice from a security company that you'll get when you're writing crypto code. So I'm going to use these. This is my assumption going forward. And then we're going to take a look at, even given advice that we all give to everybody, what goes wrong. So our code will look more like this when we're done. So we changed a little bit. we have, we're going to load a key from the key store, and that code's not here, but I'll show it to you later. We start with AES. We use cipher block chaining mode. We generate an IV unique to the message, and then we put the IV along with the encrypted bytes in the message and send it along. So we've basically done this reasonable default here. So that's all good and well. It turns out this is hard, because for the sake of getting on the slide, I actually didn't do one other thing. What didn't I do? One thing I missed. So I've done the encryption, and there's one more step to the encryption to making it proper I didn't do. Hey, go ahead. Yep, so I didn't verify the message. So integrity is important. We want to make sure nothing changed. So I didn't HMAC it. That's a separate step with CBC. It's all in one GCM. But, like I said, more to worry about. Now, for this talk, we're going to settle knowing that there's more to do with this equation. I'm not going to implement that now because I want to focus on the other piece, which is the sensitive data stuff kind of being inside of memory. And the last thing is I'm going to take some code and we're going to make a little HTTP service to encrypt and decrypt. So we'll take our code and we'll make it useful. We'll make a soft HSM, if you will, that somebody can call. So it looks like this. You give it some data, it gives you back some encrypted data. You give it some encrypted data, it gives you back decrypted data, right? Simple, nothing to it, that's all it is. With this, we call our data safe. We have now encrypted, it's secure. I said nothing about key management, but that's a whole separate problem. But in reality, this is not the case, right? This is not safe at all. What I'll show you is interesting. When we dive in, it'll be a little bit more interesting as we hit our roadblocks. But we have a huge, huge problem with this. Just those two, calling those two endpoints. That's all I did. I'll show you kind of how many, but the heap gets littered with this data all over the place. Right? Every time we've done something, we put data on the heap. We put it in memory. It's managed memory by the runtime. We don't have control of that memory. You can't tell it to go away. You're kind of relying on the host on the host virtual machine to do this. You have no control. So you can guarantee the encryption keys are in memory. But what's startling is how many times and how many places they're in memory. Decrypted data, those sensitive values, they're in memory, right? How many of you use strings in Java? If you do, those aren't going away. Now, there's a chance that they live in Eden, they won't get promoted out of the ephemeral garbage space, and effectively they'll get garbage collected soon. Young garbage is cheap to collect, it can be done in parallel, it's pretty easy. You're not going to end up in metaspace or any of those weird things that have happened. But the proliferation of data is much, much worse. Because these virtual machines have gotten so efficient, the way they make use of memory is by copying things around, moving them around, reallocating memory, sorting it out. It's all about optimization for the runtime. So as this optimization for the runtime happen, we lose control of the data. So that instance of byte array of data you had, you might have a reference to that. But the virtual machine might have made 4 or 5 copies of it so that it could kind of move it around and optimize it, and those haven't been cleaned up. And so those are instances you don't have control of. And that's kind of the problem that we want to dig into. So example, you saw a little curl request, and one to encrypt and one to decrypt. I did that once, I paused the VM, and I took a heap dump. So just give me what's in memory right now. So the little query at the bottom here is basically show me the key in memory. So it's show me from every instance of byte array with a length of 16, the size of our key, and the first value is -28 and the last is 6, which I happen to know are the starting and ending value of the key. So show me the key in memory. Those are all the results. 2 calls to this HTTP endpoint, and the key is in memory that many times. So we can take a look. Take a quick look at this. I just picked one at random. And I look here, and there's a bunch of stuff, but it says, I have a reference to a byte array, and it's part of embedded cipher, part of the cipher block chaining mode. It's basically down in the bowels of JCE. And the encryption key is sitting in there. You can have lots of different things. I'll show you some of the other ways it gets trapped in there. But this is kind of startling, right? This is interesting. What we want to do is figure out how we get rid of it. Now, I want to take a couple of minutes, because we don't have tons of time, and kind of go through and figure out how we got here. So what I wanted to do when I built this example was use no libraries. So other than the common Java libraries. So in this code, the only library you'll see that isn't part of the default Java is some logging stuff, but that was more just for building. And we'll take a quick look. Oh, my screensaver's saying it. Yeah, that's good. Let me mirror my displays here. So let's go from the outside in. So let me know when you guys can see this okay. Is this big enough, small enough? Okay. So, get rid of that. So what we have is, and this is the important part for this piece, right, is our server. This is what we start when we start the process. Handling nonsense, but right here is what we actually care about, which is basically we're going to listen on a socket and block. We're going to read the request. I'm going to write a response. This is the server. This is a in Java plain HTTP server. It's riddled with problems, but it's part of my example. It's very, very small. The read request stuff is just decorating and dressing. The handler is actually what we care about. And so when we handle requests, we just figure out what method it is, and they kind of dispatch out. And so the relevant pieces here are when we have encrypt and decrypt, it just calls into our crypto library and does encrypt and decrypt. Now, because most people try to make this nice and efficient, all the things in crypto are, it's all static. There's no objects get invoked except for the stuff underneath. So I'm not making a new world and trying to keep it efficient that way. So we have encrypt. And encrypt looks mostly like it does on that slide. The only difference is I've done some of the byte packing and stuff in other methods down below to kind of keep it small and simple. But this is effectively the code that gets rendered here. So we see that we call load key, and we assign it to byte array. So that's one instance of it hanging around in the heap. Now, if we go down to the bottom here, load key is another function. And this is just awful, terrible Java code, but this is mostly to prove a point. So we call in a properties file. So we're going to have some sensitive data in for our properties file. We have key store location, key store alias, key store password, right? So the password for the key store is going to be in memory. When we read in our Java or JCE key store, we're going to end up having the key store itself loaded in memory and then kind of opened up with the password. This is going to create a few more instances of sensitive data in the heap as well. So what we're seeing here is basically a bunch of places where stuff's going to end up getting put in. Now, this is only Java code from the Java standard library that I wrote in a very small amount. I mean, this is what, maybe a couple hundred lines of code total for all this stuff. So we already have this much proliferation, and I was trying to keep it small, right? How many of you build stuff in like, I don't know, you have a big Spring thing or a big JBoss thing or WebSphere or WebLogic or any of those big giant, J2EE container, world frameworks. Do you have any idea what's happening there? If you take a look at any of those, it's worse. Thousands and thousands of versions of this laying around in the heap. So I'm not picking on any one in particular, just saying that once you get bigger, this stuff gets much, much worse. So what I want to do is focus on the encryption key, just the encryption key. Only because we have a shot at managing the encryption key, because it doesn't ever come in as a string. The other stuff, it's probably going to get converted to a string at some point, so that's a whole different story. But if we look at just dealing with the encryption key, we might have a shot. So load key from key store. This is a piece of code that I wrote just to isolate what happens when we load a key from the key store. It's not doing any encryption at all, it's just loading a key. So we find the key store in our path. We give it an alias for our key here. We give it a password. We grab it, we load it, and we assign the byte array here. So we have one instance, or we should have one instance of the key in memory. What we've done is say, load me a key from the key store. And then we do our thing. So we run this code, and we take a heap dump. 2 instances of our key in the key store. Anybody know why? Anybody guesses why? So if we look, and if you can't read this, I apologize. On the left, the reference is this. This is the key store we assigned. Basically, it's the context for the object. So on the left is the expected instance of the key store in memory. On the right, if we dig in, we have a reference from secret key spec. So the underlying library, the Java key store library, creates an instance of the key in memory that you can't control. So if we use key store, like the recommendation says in memory, this happens. So recommended reading on this subject actually gets you in trouble. So there's one thing here, though. So if we look under each one of these pieces of data, we see something called no references. Anybody know what that means? No references means nothing is currently trying to access this data. Nothing is holding on to it. There's no pointers back to it. No other piece of program execution. No stack frames are pointing back to this piece in memory. So in a world where you have a managed runtime as a garbage collector, what is this a candidate for? Garbage collection. So we think to ourselves, that's wonderful. I have this thing that got created, but I can't control it, but there's no references to it. So I just do this. Now, this solves all of our problems, right? I see one person smiling and nodding. To catch everybody else up, there are many things wrong with this. First of all, this in your code is merely a suggestion. It actually does nothing. You can actually turn on the JVM and say, don't permit this. Like if you invoke the JVM with some flags and say, don't allow manual GC, it'll just ignore this entirely. And if it's in the middle of another garbage collect operation, it'll ignore it. A whole bunch of things happen here. But effectively, this is a suggestion. The other thing that happens here is when you force garbage collection manually, you have a pause. It has to do with the garbage collect operation. So you now incur a performance penalty. So a thing that may or may not work that invokes a performance penalty is usually not what you want to do to solve a problem, because you actually haven't solved any problem yet. But if we do it, and it actually succeeds, we're down to just this one instance, which is the one that we have in memory, the one we've actually assigned. So let's pretend that actually worked. We go in, we look at it, but we still have the same problem. This is still in memory. So what will we do to take care of it? What's the natural thing? We have a byte array that has a value. We can't delete it, but what will we actually do? What's the thing that we would do to deal with that? Yeah, you override it, you zero it out, make sure it's kind of cleared. Because in Java, byte arrays are mutable, so you can actually change them. So we could delete it, make the call directory. So other thing we could do is actually make a optimization here. We could just not assign it. We could, instead of assigning it to a variable, we could just plop in the key store load function, and the assignment would actually go away entirely. So that's always nice. Then you have kind of uglier code. So well-factored code that's been broken apart will cause this to happen more often, because you're putting more things, more assignments on the heap. Now, Java's kind of good with escape analysis. It might leave things on the stack directly and not actually put them on the heap if it's small enough. So Hotspot's pretty good at that stuff. But either way, let's pretend you're going to be left holding this, because in a bigger code base, you are. So, like I said, more complicated examples, they hold on to that byte array anyways. So we need to clear it. We do this. So we can say arrays.fill. So say, just take that array and fill it with zeros. Mem set 0. And if we do that, we now have a heap that's free of our key after it's been used. So we've done all this exercise, all this work, but what's wrong? We still have something that's wrong here. We talked about system.gc. There's something else that's wrong with arrays.fill. Two big things, actually. There's one obvious thing here. So arrays.fill is a suggestion again. If you have assignment, and then you do something to a thing, and then you never ask for it ever again, what do you have? To an optimizing compiler or an optimizing runtime, what do you have? You have dead code, right? Code that doesn't actually need to execute. This arrays.fill that's sitting here, we never actually ask for the variable again. So the optimizing compiler will just say, I got your back. I'll take care of this. Let's just get rid of it, right? GCC does it. Java will do it. The CLR will do it, right? This is an optimization. It's a dangling reference, and it has no access anymore. So you had a good intention here. You tried to do this. However, the compiler and the runtimes are smarter than you are, TM, so they will take care of it for you. Now, when you do that, that's a problem, because eventually, maybe the first couple of times this will run, it'll be fine. Once it catches on, it'll go, oh, wait, hold on, we're never calling this code. We're never actually executing this. We don't need it anymore, so let's just get rid of it for you. So we can't fix keystore.load. That's part of the Java ecosystem. We could write a patch for it and sit in an expert group and file a JSR and do all of the million steps you have to do to get change of the language done. Or we kind of realize the inevitable, right? We either have to invoke garbage collector or stop using key stores. Neither one of them is a good solution. That's a problem. But we can go a little bit further. We can take a shot at zeroing the byte array. So let's say we stop using key stores and start using things directly. We could actually take a shot at zeroing the byte array and making sure it will actually run. So what's our next logical step here? If we can't do it in Java, we do it in what? Yeah, we do it in C. So we write a JNI extension. And so we copy and paste Colin Percival's guarantee to not be optimized away by GCC memset code, which effectively just does some tricks with the compiler to make sure it doesn't forget about it. We do that, and then we call it down here. This is some C interop for Java that you may compile up and use in your Java code. What it effectively does is it calls something called get primitive array critical. Basically, grab me this piece in memory and hold on to it. Nobody can touch it. Not even the garbage collector can touch this code while I'm doing this. And then go ahead and call my secure erase or my secure zero, whatever we want to call it, and guarantee that this will be erased. So I do that, and then I put it in my Java code. So I load this library that I've got, and then I expose a little method called zero. And then in our key store, in that little piece of code we had, we call this, we print the array, then we call our secure erase. So we know that we're going to go all the way down to C to this. We're going to set the memory, and we know we won't get optimized away. It's all great. But what are we missing? So we know that this will ensure the operation will not get optimized away, right? We know it's going to execute. It's positive. We're missing one more thing. What doesn't it solve? We talked about this already. What doesn't it solve? Yep. So still laying out on the heap, right? The runtime will still make copies. Copies you don't have access to, don't control over, whatever, right? We zero out the thing we have access to. But it doesn't mean that we zero out all the references to it. Now, sometimes the runtime's smart enough to realize things have changed or gotten zeroed away, and we'll delete the references and collect them away. But we don't have deterministic control over that. So, bad. And we're loading keys from a file on disk, which is way worse than the problem we have in memory. So there's that problem. But I told you we weren't going to solve key management, because we could probably be here for the next 8 hours and still not have a real good solution. So, also a problem. So it sucks to do it from the regular, kind of recommended reading. We've gone all the way down to C. It doesn't solve our problem. What is the other thing we can do that doesn't involve being on the heap? We can actually go off heap. So Java has a few mechanisms for going directly into memory off heap. You control it. It's out of the runtime's purview, basically. So we can try this. We can do something called a byte buffer. The direct byte buffer is really what it is. But it is a buffer that sits off of heap in direct memory. There's a space for this allocated for the runtime on the JVM. So we load our key into this, this special place. We actually do the crypto. I left that out. And then we zero out that byte array in memory. So the runtime has no purview over this at all. This will actually guarantee that we have nothing left when we're done. So this actually does the same thing that the JNI operation did. Exact same thing, but we don't have to compile all that C nonsense. And I don't know if you've ever had to do this before, but building the C code into Java, the JNI extensions, and all the packaging and all that stuff, it is the biggest pain in the ass. I think I spent like 5 hours trying to make this work in this little Maven package example, and I just gave it up and wrote a makefile. But same effect, but it also prevents the scattering of data. So there's same effect as the JNI operation, but it gives you more control. So you end up with kind of what you really want at the end of the day. So that's fantastic. But we still have a problem, right? We don't have total control of the data. Because this works when you can control loading a file, and basically the whole pipe for getting stuff into memory, you have complete access over. So this is fine, but we can't put the key store off heap. Right? You can't put an object off heap. You can only put scalars, basically primitive values. Anything primitive is subject for being off heap, but any kind of object that's constructed can't be serialized off heap. Just not a thing. So there's stuff that's coming that may allow us to do that in the future, packed objects, other things like that. That's more the IBM JDK than the Sun or Oracle JDK. But we still can't put objects off heap. So all that work, and we're still kind of left in a weird place. It doesn't actually solve our problem. So let's take a quick minute and talk about where we're at. So we want to encrypt things. We really want to encrypt things. We can do nothing. We could just write our code, recommend it, and go. We just see what happens there. We leave a lot on the heap there. Calling systems.gc is heavy and unpredictable. We actually don't know what's going to really work, and it's going to cause a lot of performance issues. How many of you have ever profiled your garbage collection and figured out what the length of the pause is? Anybody know what your pause is on a regular basis? Anybody ever have performance profiles that will spike like once or twice a day, and all of a sudden like 10 milliseconds, 10 milliseconds, 10 milliseconds, 5 seconds, and then it'll happen kind of in a weird direction. That's the garbage collector doing its work. And if you really try hard, you can invoke it manually at certain times and do really weird tricks, and this happens all the time in like trading industry and that kind of stuff. But playing with the garbage collector is basically dancing with fire. So JNI is cool, but it's a pain. It does prevent the unwanted optimization, but it doesn't prevent things being scattered across the heap. But the good thing is you can actually do the kind of direct byte buffer approach, and that does do the same thing that the JNI operation will do. But you can't put objects off the heap. And the other thing is key management is hard. We'll put that down there. That's nothing to do with our talk, but we'll keep saying that because I'll pretend like we'll solve it someday. But we want to know now what. So we've talked about a bunch of stuff that doesn't work. And a bunch of complicated stuff that doesn't work, to be honest. At the end of the day, this is more effort than I want to have to put in to encrypt and decrypt. It really is. I mean, my full-time job is writing software. It happens to be security-focused software, but it's software. And at the end of the day, if I have to do all this stuff and I'm still not good, I don't care, right? This is a weird problem for me, is what's the value I'm getting out of all this nonsense? And the answer is nothing. I'm not getting any value out of this. I haven't solved my problem, and I've taken a bunch of steps that don't matter. So we're still not there yet. Like, what we have, even after all this time and energy, is not good enough. So we don't have a solution to this problem. Anybody know what the real answer is to this? Yes. Yeah, there's that. That's a good thing. And so you've hit one other piece here, right? Dedicated processor. How many cores does your CPU have right now? Let's say the standard newish Xeon processors, like Broadwell, Haswell, newish processors. How many cores on these boxes? 64. I mean, even the cheap ones are 24 at this point, right? Anybody know how much level 3 cache is on each one of those cores? Megabytes of cache, like lots of cache. Oh, I know. But I have a point here. Is when you do this, let's say you write some code. We want to manage runtime. We have really good things like optimizing compilers. The CPU optimizes everything away. Let's say you're hitting this stuff a bunch for encrypt and decrypt. Eventually, what's going to happen? You're going to end up with this data in cache lines in the CPU. Right? It's just going to happen. Can anybody here deterministically predict what happens when a context switch happens, what gets cleared off your CPU, right? In a managed runtime. Unless you've basically gone to assembly language inside of your JVM operation, you can't predict it. And even the assembly language that you write is not the assembly language that gets run on the newer processors. It gets divided up, it gets rewritten, all kinds of stuff happens. It's really complicated now. The cool thing is that AES is actually built into chips these days. So you could technically actually go all the way down to the assembly language and pipe this through the processor, which that's kind of cool, right? That's a good thing. But you're all the way down there, and that's rough. But if you look at the things like this computer, right, has file vaults. File vault is going to run a bunch of disk encryption, and that's going to run on chip, right? So Apple's done that, and that's great. I like that. I don't think anybody's really done a really good job at kind of getting those encryption keys back. They've done some cool stuff with hardware there, but in general, you don't have this. You have a server sitting somewhere, and yes, you could do it all on one server or all on a cluster of servers. That's actually kind of more realistic, right? You protect the access to those servers more than you protect the access to different servers. It's restricted. There's certain things that can talk to it. Now we're talking about the problems that I wasn't trying to solve, which is basically perimeter approach and how you secure the box. We do actually need a solution, right? For now, it actually is more about looking elsewhere. So the managed runtimes are awesome for writing lots of different code. Maybe not so great for this kind of application, right? This goes all the way back to the initial question, right? Would it have been better if OpenSSL was written in Java or C#, right? Kind of managed runtime that would prevent what happened in Heartbleed actually solve our problem. And the answer right now is no, right? It prevents the class of problems that cause Heartbleed. It introduces an entirely different class of problems that we just saw here. So there's trade-offs, right? Now, the good news is we don't have to do it in C. We don't. How many of you really, really, really like programming in C? I actually do I do it in my job quite a bit, but nobody really likes, oh yeah, I'm so excited I get to go write C today. No, that's not a thing. Some people will do it for their job. That is their job, but not many people enjoy doing it. There's Rust, there's Go, new languages that come around that are still, they're still maturing, right? I think Go may be a little bit better in production than Rust is at this point. We actually do use Go in production. And quite a few companies do too. But it means finding a thing that doesn't have that really crazy managed runtime that still doesn't make you work really, really hard for this crypto to work right. And Go actually has some nice libraries for it. So it means looking elsewhere in the times where you have handle sensitive information, right? It's guaranteeing using safe handling of data. And it means just being able to kind of bend on those rules. How many of you have thought about that or kind of done that in general for the crypto? What was the giant thing I didn't talk about at all yet? I know some of you are probably using. Who said that? Yes. So, better yet, use an HSM. Seriously. I mean, this is actually, this is the thing that actually keeps it all safe. HSMs are the standard, default, de facto, generic, this will kind of work. For those of you who have never heard of an HSM, hardware security module. It's a lot of different things. It takes a lot of different forms, right? But stick it in a rack. Usually it's a network-based thing. You plug it in. You feed data in and out. It holds your keys. It does the crypto. It does it all in this little magic box, right? The keys are hidden there. It's tamper-proof. Somebody tries to break it open, there's pressure switches that will just dump the memory. So whatever keys were there get lost. So it's actually going to keep that stuff safe. It comes in the form of, you can put a PCI card that has the same kind of stuff built into it and stick it in a box in the rack. They have USB one. There's all kinds of different ways of doing it. Actually, I think SafeNet's here, aren't they? This is our sponsor. They make a product called Luna, which, has anybody heard of Amazon's HSM or key management stuff? Luna, I'm pretty sure Luna drives all that stuff at AWS. So if you do the AWS version of this, which is totally cool, I'm pretty sure they're running the Luna stuff for all their stuff at Amazon. I don't know 100%, but I'm pretty sure that's the guy, because I remember running it once and seeing a Luna agent running on a box. But really, having something like that is great. Now, the trade-off to this is they're really expensive. Really expensive. Doing it right means having multiple per data center. How many have more than one data center? How many have more than 5 data centers? Yeah, so two of these per data center at a minimum, right? Assuming that one is enough to do all your traffic. So, 2 at a minimum times 5 or more times 80 to 100K for each one, right? You're well over $1 million early in, right? And that's just the expenditure for the boxes. You still have to stack them, you have to operate them, packets and power, the whole deal. The total cost of ownership for HSMs is big. So it's very hard to ask for that money, right? You basically say, oh, I have crypto already. Great. We've encrypted everything. Oh, no, but I'm not doing good enough yet, so I need a couple $1 million so I can do it better. And that's just like, you know, people look at you cross-eyed and look funny, and then you start talking about twiddly bits, like what happens in memory, and all is lost, right? Now, on the other side of that world, you have some case studies that work. Things like, you know, kind of the semi-popular health insurance breach that happened recently. They blamed crypto, right? I don't blame crypto. They blame crypto. But honestly, even if you had crypto in that situation, and they were doing it there, the attackers are already in the network on the machines, right? Okay, great. They got everything anyways. All you got to do is look a little bit harder, right? That's when this kind of segregation becomes a little bit more important. And so, you know, it's a risk appetite thing. We'll go back to the keynote, right? It's a risk appetite thing. What's your intent? What are you trying to solve? What are you actually protecting, and how much does it matter, right? Is it worth spending $1 million to protect it? Because the chances are you probably spent a few $100,000 in developer time to build whatever you had now. Or maybe you hired a consulting company, whatever it is, right? You've already invested 6 figures, at least, in this solution, whatever it was. But you know, now you want to justify maybe 10x or more increase in cost for this. And by the way, it's a black box that you actually don't know anything about. So that's a risk too, right? What happens when like you have to build up expertise, training, hiring people to administer these things. It becomes it's a bigger cost, right? It really is. But at the end of the day, if I had to bet any money on any kind of solution and know it was effective, this is where I'd put my money. Right? If I started from scratch, I go straight to this. And you could offset the cost. If you don't want to spend a couple $1 million in infrastructure now, Amazon's solution is great. It's like $5K or so to rent an HSM, and then you pay per time. You can use the HSM straight up, or they have a thing called KMS, the Key Management Service, which basically is just backed by those HSMs anyways. And there's this API just for keys and just for data encryption. So you can actually go even smaller and get charged for just those crypto operations. You're basically segregated out. The way they work is you get kind of virtual HSMs within a single networked HSM, and you have your own kind of private little instance of an HSM that's only so big. But you can offset the cost by going there first. And maybe try it out once you have it established, once you've kind of tested it and know it's reasonable, then you can kind of work your way into infrastructure and maybe cut it over one by one as each data set kind of goes off of there, right? You kind of split the traffic off, and you design it well, basically. And so you have a chance to try it for a little bit cheaper, right? We're talking about 5 figures versus 7, 8 figures, right? And so it's a better approach for trying this stuff out. Some of you aren't allowed to use Amazon. I get it. I would challenge it, honestly. Amazon has changed quite a bit. The compliance they have now, I mean, the government's using them. They are PCI Level 1 certified, HIPAA, SAS 70 Type 2, SSA 16, like every single bit of nonsense, gobbledygook letters and numbers, Amazon has them all. So I don't work for Amazon. I'm not trying to endorse anything, but I would push back a little bit and see if there's a way to get them in if you really want to try this out, because it's a nice, effective, cheap way to get to a better solution. So I have a bunch more code here, and I don't want to spend too much time diving in it, but I want to pause for just a minute and take some questions, because we only have a little bit more time left. But there's a bunch of questions. I saw people shaking their heads. So in the back, in the blue, yes, you. Okay, so the question was, would something like Veracode find instances of this stuff being put in the wrong place? I don't actually know. I've never used Veracode's product for that reason. If they're here, actually, I think one of the speakers is from Veracode here. I would ask them and see if that's an option. My guess, if I had to take a guess, is no, unless there were some custom rules you could write, because unless you can mark something as sensitive, it's just another piece of program code, right? You could look for instances of key store and the JCA being invoked and those kind of things, but once you're past the base classes that do the crypto, and that information is passed along, it's out of scope for Veracode to really actually see unless it can actually see where it came from. So it's pretty deep program analysis if they can do that. And my guess would be probably not, but you should totally ask them. I really don't know. It might be, yes. Knowing that would be great. I don't have any good tools to do that. There is one company called Contrast Security. They're doing dynamic runtime analysis. Have anybody ever heard of like New Relic? You drop in agents, basically. They run at runtime. They analyze the performance of the code. Same idea. You drop it in and runs it as an agent. And as it sees like unprotected strings hitting a database driver, it'll flag it and say, oh, you have a SQL injection. And you don't have to attack it. You just run your code normally. And it will see that, oh, and this is bytecode level. It analyzes it, runs it. It sees the unprotected string hitting the database driver and going, oh, wait, yeah, that's a SQL injection. I can guarantee it because you executed it. And so that might be a better one where they would mark certain execution points in the runtime. I'm pretty sure they don't do that either. Yeah, but if I had to bet on something, that's what I would bet on is that runtime analysis piece because it's not so much about the code, the static analysis piece, but what actually got executed. What did Hotspot do to that code and then execute down the road? Because that's the stuff you don't have control over. Does that make sense? Yeah. Sure. Mm-hmm. Mm-hmm. Sure. Yeah. Yes. Yeah, so the question is PHIPPS. So PHIPPS 140 is probably what you're after. Yeah, so if you're in that PHIPPS land, how do you deal with that, right? Yes, OpenSSL has PHIPPS compliance, PHIPPS 140 for compliance stuff you can grab. The OpenSSL group has consultancy set up around that. We've all seen what happens to OpenSSL over time. I don't trust it very much. But the HSMs that I talked about, you can run them in any compliance mode you want to. Almost every HSM I've ever talked to has a PHIPPS 140-2 compliance operating mode. So you just turn the thing on and say, I'm operating this mode. And they will do all of the compliance mandated things around crypto. So as far as I've seen that every other time, it's just turn it on. In the HSM space, anyways. Keep going. No, keep asking. The PHIPPS modules you pay for. Yeah, so some of it, right? Yes, some of it, yes. Not all of it, right? Yes, Heartbleed and all that stuff, that was in the open sourced, kind of standard package of OpenSSL. But, yeah, so you talk about the I/O layer, right? Most of the HSM products that I've seen, the agents that run underneath, have either that or some kind of other custom thing similar to that runs underneath for those, the established connection calls. Heartbleed, even with the PHIPPS I/O modules, wouldn't have done anything because it was a memory allocation problem. Basically, it was allocating memory that hadn't been, it was overrunning memory that hadn't really been allocated by that control block. And so you'd extend past it. And the way OpenSSL's memory allocation worked, it's custom because it has to try to account for a bunch of different platforms. Basically, returns you pieces from memory that hadn't been cleared yet. So there was a call to malloc that could have been solved by a call to calloc, right? so which actually zeroes things out, but is slower and more expensive. It doesn't run on like VMS, right? Which most of us don't care about anymore. But things like that prevented OpenSSL from doing the right thing there. And so it was just a memory allocation problem. Is there, I think you had a question? Sure. Yeah. Yep. Sure. Yeah, the question is, what's the threat model? This is a lot of work when we could probably throw it away. It may not be valuable enough to do this work, basically, right? Depending on what your threat is. This is, of course, an inside threat, right? Somebody has to have access, physical access to a machine, or login access. They have to be logged into a machine to get this memory. That's not exactly true in every case, though. So, I will present to you a very, very common case. I boot up my Java application, and I throw it in Tomcat. And I turn Tomcat on with heap dumps when it crashes. So generate me a report of the memory profile when it crashed, and throw it in an available place. And I put it behind Apache because I want to make sure Nginx is something that lets me front it with a nice little port 80 thing. And I turn on directory indexing. What just happened? Right? I just made my heap dump accessible to the whole world. This happens a lot. I mean, a lot. Misconfigured Apache is a huge problem. So you turn heap dumps on, you turn on indexing, all of a sudden people can get to your heap dumps. And it's really, really, really easy to make one of those applications crash. You just give them too much information. Just overload them, right? A single machine can usually cause enough load to generate to crash a Java app. That's not properly protected or put up. So you crash it, the heap dump goes in the path, you download it. Right, so this is an actual likely threat scenario, which is just standard, denial of service based attacker. It is truly a remote attacker, right? It is not an inside attacker. It's a truly remote attack. So that is a very possible threat scenario. Oh yeah, totally. Yes, I mean configure it properly, and this problem goes away. Yeah. And so don't turn on heap dumps in production unless you're really sure that you're not going to get, somebody's not going to be able to get them. Now, the other thing is there is a bunch of things that matter here that are not our web server, right? How many of you have an Android phone? Okay, how do they solve that problem? Yeah, I know. It's really scary, but, right, Android this is Java. All the apps are in Java for Android. There's some C. There's a little bit of Linux kernel underneath, but it's Java, right? Your set-top box, your cable box, right? I know we have questionable motives there, but you're trying to protect that copyrighted information from leaving that box. You can assume physical access because it's sitting in everybody's homes, right? Things like that are more likely, like, this is a kind of general threat scenario, but assume physical access because they have them. Assume physical access to your phone because somebody has it, right? So there's more applications than you would think for physical access here. So the threat scenario is somebody, of course, has some physical access aside from the remote thing I just talked about. But it's more common than people think. And it depends on the industry you're in and what you're trying to protect, right? That's where you have to start. Yep, that's absolutely right. And like I said, the only thing I want to talk about is what happens at runtime. All those other problems they're left to be solved. They are, right? But we could spend all day looking at each layer of this, and we're still going to be, left with a bunch of missing pieces of information. So, yes, you have to assume. Yeah. Yep. Yep. Totally. Exactly right. Yeah, absolutely. That's totally valid, right? All of those pieces, once you're on the box, are game, right? They're fodder for doing this, and you have to take a look at which pieces you really want to spend the effort to protect, right? Once you get in here, the HSM agent solves a lot of those problems, right? Things don't go in properties files anymore. Things don't go into those different places. You end up with a more holistic solution to the problem, right? You can one-off all of these different things that you want to, but at the end of the day, you're spending a ton of energy fighting a problem that doesn't actually have anything to do with your core business. How many of you have a core business model that includes encrypting things? If you work for SafeNet, you can raise your hand, but otherwise, probably not, right? At the end of the day, it's about business value. If I'm spending all my time trying to do a bunch of one-off stuff to do crypto right, I'm not solving business problems. I'm simply lowering risk, which is a business problem. I'll acknowledge it, but our core business models and the companies we work for are not solving this problem, which is why I totally suggest just paying money to make the problem go away. Yes, absolutely. Getting crypto right, even if you go drop down to C or Go or Rust or any of those things, it's still hard to get right. You're still probably going to get it wrong, right? Even if you end up doing it, you want somebody to audit it. Somebody that really understands the stuff should audit it. And I don't know too many people to recommend people to for those kind of audits. There's a very small group of firms that are capable of doing those kind of audits effectively. A lot of people say they are, but there's really only a few that can really do it well. Okay. You're absolutely right. Yep. There's a whole other class of problems that are important to solve there too. So, if there's any more questions, I will be out in the hallway, but I want to take a little bit of time to let the room clear out and all that. So, thank you very much.